Hello, and today's purpose of the day is I can identify, use, and graph inverse variation. So here's a little summary on direct and inverse variation. As you can see with direct variation, y equals k times x is the equation for that. Y varies directly as x, and the ratio y over x is a constant. So as you look at under direct variation, the two graphs, you notice that direct variation, as you already recall, is a straight line. So the first graph is when k is greater than 0. So in y equals kx, k is like our slope. So when k is greater than 0, obviously that line or that graph is going to have a positive slope, and so that's going to increase as you look from left to right on the graph. The other graph, k is less than 0, has a slope that is obviously less than 0. Therefore, the graph is decreasing or has a negative slope as you look at that from left to right. Now, as we look at inverse variation on the right side, we have y equals k over x for the equation, or this could be represented as x times y equals k. So those are the two forms that we reviewed together with inverse variation. Y varies inversely as x does, and the product x times y is a constant. So as you look at the two graphs, they are graphs that look like, a little bit like parabolas, right? And as you notice on the top left-hand graph, when k is greater than 0, you have graphs that are in the first quadrant and third quadrant. So again, when that constant is greater than 0, and this will always be, your graphs are in the first and third quadrant. If k is less than 0, this is like its opposite. The two graphs are in quadrants 2 and 4. So something to write down and make a note. So when we practice graphing on the next couple slides, if k is greater than 0, again, my graphs are in the first and third quadrant. And if k is less than 0, my graphs are in the second and fourth quadrant. And we'll talk more about what these graphs are called and why there are two graphs for inverse variation. So a little bit of review. Determine whether each table or equation represents an inverse or direct variation. Explain. So as we look at table 1, I see that x has 1, 2, and 3, and y has 3, 6, and 9. So as the x values increase, the y values also increase. So that was one of the requirements we said with inverse variation, right? As one of the values increases, the other should be decreasing. That's not happening here. Let's see if x times y equals a constant each time with all of the ordered pairs. Well, 1 times 3 is 3, 2 times 6 is 12, 3 times 9 is 27, so obviously that doesn't work. So they don't equal or multiply to be the same constant. So we could think that this would probably be direct variation, and a way to explain again is by an equation. So let's see what's happening here. I could plug in a point, and say, and figure out for k. So I could say 3 equals k times x. Okay, so 3 equals k times 1. So 3 equals k. So my equation or my explanation too would be y equals 3x. All right, let's look at number 2. Y equals 6x. This one is actually, fairly simple. This is already in one of the forms. This is already in direct variation form because it's y equals k times x. So this one's very simple to explain. We would just say this would be direct because y equals 6x. Number 3, x times y equals 15. Well, this one too is already in one of the forms. Hopefully you recognize that this was already in the inverse variation form. So a way to explain would be inverse because xy equals 15. That's, again, already in the setup equation for inverse variation. All right, so a little bit more review. Assume that y varies inversely as x. Write an inverse variation equation that relates x and y, then solve. So here, as you recall from the other day, we could use either the product rule or setting up a proportion. And so I will use what method I think is the simplest for myself, but again, you could use whatever one you would like. So here on number 4, if y equals 10 when x equals 5, find y when x equals 2. So I know that with inverse variation, x times y equals a constant. So I could say here, 10 times 5 is 50, and that's got to equal what my next two variables multiply to be, the same constant, so equals 2 times y. And now we would solve for y by dividing by 2, so y here would equal 25. All right, number 5, if y equals 8 when x equals 2, find y when x equals 4. So again, same setup, xy equals a constant, so 8 times 2 equals 16. That's going to equal 4 times y. Now I solve for y, and I get y equals 4. Number 6, if y equals 100 when x equals 120, find x when y equals 20. So x times y here is 12,000. That equals 20x. Divide by 20, x equals 600. Number 7, if y equals negative 16 when x equals 4, find x when y equals 32. So negative 16 times 4 is negative 64 equals 32x. X equals negative 2. Again, these aren't difficult when you have a method down. They go pretty quick and, like I said, not too difficult. Last one, number 8, just for some practice. If y equals negative 7.5 when x equals 25, find y when x equals 5. So negative 7.5 times 25 is negative 187.5. And that's got to equal 5 times y, divide by 5, and y equals negative 37.5. So again, nothing too difficult, just a little recap from yesterday. Now we are going to look at graphing inverse variation. So we are going to write an inverse variation equation for the data. We'll make a table and use reasonable values to graph, and plot points and connect with a smooth curve. So as you could recall from the last slide, when you looked at the graph of inverse variation, you saw that there were 2 graphs and they were like parabolas, but there's 2 of them. We call this now a hyperbola, and for us this is going to be like 2 mirrored parabolas today. So we actually have 2 graphs that we will be making here for inverse variation, and again it's called a hyperbola. So let's look at number 1. So here on number 1, I see y equals 9 when x equals negative 3. So my equation that I'm going to write, my inverse variation equation, is x times y equals, now what does 9 times negative 3 equal? Negative 27. So that's my constant here of variation. So now when I want to graph this, let's plug in points in our table and actually then go plot those points in our graph. So let's think of what multiplies to be negative 27. Well, I could choose 3 and negative 9. I could choose negative 3 and positive 9, 9 and negative 3. I could choose negative 9 and positive 3. And again, I know looks like I'm doubling up on some ordered pairs, but as you can see, there are different values in for x and different values in for y. So as long as I have a few positive and negative values, that's good, because then I'll then be able to actually plot both of my hyperbolas. I could also use 1 and negative 27, or negative 27 and positive 1. Again, I don't need to plug in a ton of points, but I want to get a good number so I can graph. So now let's go ahead and graph those points on our graph here to the left. So I've just plotted a few points over on the left of my graph, and so you can see that they are in opposite quadrants. Here it's in quadrants 2 and 4, and if you can recall from the notes that we just looked at, that when your constant is a negative, your graph should be in quadrants 2 and 4, which is a good thing just to check. So let's actually connect these points and make our hyperbola. And there would be my graph for when y equals 9 and x equals negative 3 for inverse variation. All right, number 2, y equals 12 when x equals 4. So let's write an inverse variation equation. So xy equals 48. Now this constant is positive, whereas we saw in the last example it was negative, and our graphs were in quadrants 2 and 4. So this graph, since it's the constant is positive, our graph should be in 1 and 3. So that'll be a good thing to check when we're done, make sure our graphs are there. So let's fill out a table and pick some easy points. So what multiplies together to equal 48? Well, I could say 6 and 8. I could say 8 and 6 then. Just flip-flop the values for x and y. Negative 6 and negative 8. Negative 8 and negative 6. 2 and 24. Negative 2 and negative 24. So let's go plot these to our graph on the left. So as you can see that my hyperbolas are in quadrants 1 and 3, and so that would be my inverse variation graph for number 2. Number 3, y equals negative 25 when x equals 5. So here, my inverse variation equation would be xy equals negative 125. Now let's pick values for our table to plug in. So some values I could choose would be negative 5 and positive 25. I could choose positive 5 and negative 25, negative 25 and positive 5, or 25 and negative 5. And again, all I really need is a couple positive values and a couple negative values so that I can make sure that I have my hyperbolas in the correct place. All right, let's go graph those points on our graph to the left. And remember, our constant here was negative, so our graph should have been in quadrants 2 and 4, which they are. And as you recall, our graphs, as you saw from the other previous examples, don't actually cross over the axes. They don't cross over the y-axis or the x-axis, and that's because they won't ever. So we could plug in many different points, and we could see that they would never cross. So again, similar to an exponential function where they get very close to a line, but it never actually gets to that line. Same thing here, our hyperbolas will never cross over either axis. All right, and here are the graphs of inverse variation. Feel free to do number 4 on your own if you would like. Again, we just went over a few examples for inverse variation.
Thanks for listening. Have a great day. Bye-bye.